All right. So what about the standard deviation of the SDOM? And we talked about it very briefly in one of the problems before, but saying standard deviation of the sampling distribution of the mean is really long, right? And we actually end up using this standard deviation a lot. This is going to be something that comes up over and over again. And because of that, we give it a special name so that we could shortcut saying standard deviation of the sampling distribution of the mean, right? And the special name is this. It's standard error, right? That's what it's called. Deviation is the word for, how far, the sort of distance between the mean and some data point, right? That's the deviation. Error is often used sort of interchangeably with that term. How off are you from some target? The target here being the mean, right? So it doesn't mean that we've made an error, like an actual mistake. It just means, oh, how off are these data points? Okay, so that's why it's called standard error. And whenever we say standard error, what we really mean is this whole thing, the standard deviation of the sampling distribution of the mean. So we don't use the word standard error for any other standard deviations. For instance, if we calculate the standard deviation of a sample or a population, we wouldn't call it standard error. This term is only reserved for this concept. Okay, so what did we learn about the standard error when we did some of our simulations? Well, let's look again with a special focus on standard deviation. So let's go to the normal distribution, and let's start with the lowest, let's start with the n of 5, right? And let's take 10,000 simulations. And we see that, it's fairly normal, right? It's fairly normal, has a very similar mean, has a skew and kurtosis of close to 0, right? So this is looking very normal to us. But what is one thing that you notice between this and this? This one seems a lot sort of like pointier or sharper, right? So this one seems have a small, so this standard error seems to be smaller than the population standard deviation, right? And let's see if that's true for different values of n. So now let's try n of n equals 10. And I'll just skip straight to 10,000 simulations and hit another 10,000. So we see, once again, it's nice and normal. Skew and kurtosis are close to 0, similar mean. But we see that the standard deviation here is still bigger than the standard deviation down here, right? And not only that, but we see that this is even pointier than it was before, even sharper, right? Now let's try for n of 16, right? And here, I think it's hard to notice, but it's even pointier, right? It's even more like narrow in terms of its standard deviation, right? And if you notice the numbers, these numbers keep going lower and lower. Before, for n equals 5, the standard deviation was 2.23. But for n equals 10, the standard deviation is 1.61. Now, obviously, this standard deviation has not changed at all. Now let's look at standard deviation of n equals 25. Here, the standard error is 1, right? So it's really small, right? And so one thing we see is that basically the standard error is always smaller than the parent population. But not only that, how small it is seems to be related to n, right? And so let's see if that's true with other formations, right? And so maybe we'll draw a custom one. So here's a trimodal distribution. And let's try with, maybe this time we'll start off with the biggest n, so n of 25. And let's see. So the standard deviation is 1.71, and this is, looking pretty normal. But what about n equals 10? Is the standard error going to be smaller than 1.7? And it's not. It's fatter, right? And that's what we saw before. As n is smaller and smaller, the standard error is bigger and bigger, right? So there's a bigger spread. And let's try with n equals 5. We should predict that it should be even bigger, right? And that's what we see. Now with n equals 2, now the standard error is really big, right? And so maybe we'll try with one other distribution, the uniform distribution. Let's go from small to big now. So now, when n is small and getting bigger and bigger and bigger, what should happen to standard error? Standard error should get smaller and smaller and smaller. They seem to have an inverse relationship. All right. So here we start off with a pretty wide-looking standard deviation. You want to look at this red part right here. It's pretty wide, right? 6.79. But remember, 6.79 is still smaller than 9.52. So it's always smaller than the parent population, but but n matters, right? N matters. What about n equals 5? Now it's 4 point something. N equals 10. Now it's 3. N equals 25. Now it's 1.91, right? So we see a couple of things here. So standard error, and to write standard error, we would write sigma, because remember the sampling distribution is a theoretical distribution, sub x bar, to indicate it's the standard deviation of a bunch of means, right, is always smaller than standard deviation of population, right? And we call that just sigma, right? So this seems to be true. Conditions. Does n matter? Yes, n does matter. And how does it matter? So larger the n, the smaller the standard error. Now, obviously, you could also write this as the smaller the n, the larger the standard error. Same idea. And do the number of simulations matter? Does it help us become more accurate? All right, so let's see. So let's say we only had 5, right? What is the standard deviation? Well, it's still smaller. What about the n mattering? Does n matter? Oops. Let me just do 5. Right? So standard deviation is almost always smaller. That's true. So standard deviation is almost always smaller, but that's still sort of rough, right? It's like we don't know exactly how small. So it's sort of like, let's see, does number of simulations matter? Well, this is a pretty vague idea, right? It just tends to be smaller. Not really for the vague idea that the standard error is smaller than the population standard deviation. So the simulations don't really matter. But we probably want to get more precise than that. This is pretty general to just say, oh, the standard error is smaller than the standard deviation of the population. It'd be nice to know exactly how much smaller, right? All right. And that's where the central limit theorem comes in. So although we've looked at it through simulations, that's an empirical method of looking at what the properties of the sampling distribution of the mean look like. But what the central limit theorem did was it formalized those things. Like, people observed that this is true, that the shape tends to be normal as n is large, that the center tends to be similar between the SDOM as well as the population, and they also saw that the spread tends to be smaller in the SDOM than in the population, particularly as n goes up. But the central limit theorem is a formal proof of that idea. I'm not going to go over the proof, but I'll just go over what it ends with. So the central limit theorem sort of ends with this. As sample size increases, the shape of SDOM becomes more normal. Oops. I should say approximates normality. Because it's not that it's like being built and becoming more normal, like transforming, but it approximates normality, right? So as n goes up, the shape becomes more normal, right? So this is just a formal way of saying it, and they've actually proven this mathematically. And note, although it's not part of the central limit theorem, one thing to note is that the population isn't necessarily the same shape as the SDOM. The SDOM is almost always normal as long as sample size is large. But that doesn't mean that populations are always normal, right? And that's helpful to us because we know the shape of the SDOM, even though we don't know anything about the shape of the population. Okay, what about center? Well, the center, the principle of the center is this. The mean of the SDOM is equal to the mean of the population. And does n matter? No, it doesn't. What about spread? Well, here, the standard error is equal to the standard deviation of the population divided by the square root of n. The actual easier way to remember this is that the variance, the standard, so the variance of the SDOM is actually equal to the variance of the population divided by n. So standard error, right, when we square root both sides, this is going to be the variance of the standard error of the population divided by the square root of n. Right? So that's the only thing. But this will give us that nice inverse relationship. As n goes up, as n becomes bigger and bigger and bigger, you're dividing the population standard deviation by a bigger and bigger number, therefore resulting in a smaller and smaller and smaller standard error, right? As well as the opposite. As n gets smaller and smaller and smaller, let's consider the n of 1, right? When n is 1, we know that the standard error precisely equals the standard deviation of the population. And let's just think about that in our heads. If we're actually getting just an n of 1 from the population, then we'd end up sampling the population exactly as it looks, right? It would like be dropping down the same thing, right? And because of that, the standard deviation would be the same, the mean would be the same. Not only that, but the shape would be the same as the shape of the population. It wouldn't be normal. So it's helpful to think about the special case when n equals 1, right? And you would never, I mean, in statistics, you would never sample an n of just 1 because that's not helpful to us. We really get more out of the central limit theorem when n is larger and larger and larger. Okay, so this is the central limit theorem sort of in a nutshell. And this is going to be helpful to us because now we don't need a large number of simulations. Because in these, in a lot of the simulations we are looking at, the simulations sort of matter, right? Like how many simulations you do. What's nice about the fact that they've just proven the central limit theorem, also we might call it the CLT, is that now we could just skip directly to these principles without having to actually do computer-based simulations. But the computer-based simulations are helpful for us just to be able to see and know where the central limit theorem comes from empirically. All right.